Hello, Ken.
Hello.
Hey. Yeah,
Hey.
nice to see you without mask.
Yeah.
Yeah. Okay, so let's see. Let me move the camera. Just give me a second here. Okay. Camera might change a little. So I'm going to keep it zoomed out because that's how I did it last semester. And let me know if it is not easy to read, and then I'll zoom in. Okay. Let's begin with. Okay. I can remove my mask too, since there is no one in the class. So small book. Let's see. So how did you feel about the first class? Any comments in general? Anything in particular? Felt?
I guess regarding like the quiz and stuff.
Uh-huh.
I just like talked about like the history of the breakfast run. I guess I'm curious. Were you looking like for us to solve it?
No. So we will go through that in the class. That's part of the course itself. Like we will be doing a good bit on that. Now that's what again. It's a good idea to talk about the quiz. Quiz is very open-ended. Like you can spend hours and maybe even do something nice in it, and you can even do it in 5 minutes. What I suggest typically is for as far as grades go. So there is a submission part to this, there is an assessment part. For that, don't spend more than 10 minutes. But if you get curious, like apparently you looked up and you did the history part and so on, and you also thought of solving it, yes. So that is all extra. That is up to you. If you want, you should do that. That's the whole point, that you get curious and you get exposed to the subject and you're aware, okay, this exists. But I don't expect you to do so much. Just an awareness is the point. Sometimes the question might be a tricky question, so then you give it a thought on that, a critical analysis of that. Okay. So that clarifies the quiz. And could you upload it easily, the quiz? Did you upload the quiz or?
No problem uploading at all. So
Okay, good. Okay. So that is clear now, right? Because we will need to do that during the exams and homeworks and all that. So at that time, it should not be a problem. So, okay. Anything else? Oh, yeah. So I understand you did decide on the Ian electromagnetism, correct?
yeah. So I did transfer to quantum.
Yeah, I at least I noticed that you you're not there in that course anymore. So I think that might be a good decision, probably. I mean, doing a part two without part one, typically, just the notations, not just the content. Notations might be a little, might throw you off.
Yeah, yeah, for
So
sure.
that might be the case with this course also, even though you're aware of classical mechanics, that a little
Hmm.
bit of style and presentation might take some time, but you will notice that after a couple of weeks, you get a feel for what's expected, at least in this course. Okay, so let's. So I was thinking we will do some. The camera is here, but I might keep watching that side because I see you there. So
Yeah.
it's just so I get used to that. I I'll start with some simple problems on Newtonian physics, very straightforward, and I'll try to give you some help with the homework also. Did you get a chance to attempt on the homework by any chance?
No, not yet. No, I haven't. I haven't been able to do it.
Okay, so that's perfectly fine. So it is not due by the way. Okay, so let's talk about Newton's uh, laws of motion. Okay. Is it readable?
Yeah, it's readable.
Yeah. And is there a lot of echo or anything from here,
I'm
connection
not
wise?
getting much. I'm not getting much echo. So
Oh, we have, I think, Harsha. So that's Harsha. Hi, Harsha. Can you see us? Hello? I think he's still connecting, probably. Hello, Harsha. I guess he's struggling. Okay, so we will let him connect. I think we'll keep moving. Harsha, can you hear us? So he cannot even see us probably because he's not waving. Okay, yeah, but while his so Harsha is another graduate student in the department. He works in quantum information, so yeah, you will get to know people. But in this times, it is hard to get introduced to people, I suppose, right? So, but yeah, you will figure it out, I guess. Okay, so of course, Newton's law is mass times acceleration is equal to sum of forces. So let's talk about just that it's a single force acting. So this is a vector equation. And in general, the force could depend on position and time. So that's how. Harsha, can
Yeah,
you hear us?
yeah, I
Ah,
can hear you now.
there you go. Okay.
Okay.
Yeah, you struggled a little. Okay, so we had the first class on Tuesday, so that's
Yeah,
Ken.
I didn't realize we had a class on Tuesday. I'm sorry about that.
Sure, sure, that's okay. That's Ken on
Ken,
the other. He's a
hi.
new student,
hello.
so yeah, hopefully you guys get to interact with minimal interactions that is allowed in this online ways. So I'll figure out. And this, do you know the course? How to reach the course webpage, Harsha?
Yeah, yeah, I do.
Okay, so get there, and there's a syllabus, and if you there is a video recording of the first lecture, so you should be able to go there and
Okay.
get to know
On
the
on
whatever.
D2L, right?
Yeah, yes.
Okay, okay.
So go ahead and check on that. There is a homework due on Tuesday.
Okay.
That's the main
Yeah.
one. Okay. Let's do some simple problems in Newtonian physics, and then we will slowly get into how the same things can be done using the Lagrangian, right? That's what we want to do. So Newton's law is, of course, mass times acceleration is equal to force. It's typically on the right side sum of forces. So let's say that there is a single force acting on it. And now we want to talk about a few examples just to give some ideas of how to solve. First is, of course, that the force could be constant. And a classic example is that you drop a stone on the surface of the earth when you're very close to the surface of the earth. Gravity is constant, so that's a constant. Second is a simple generalization of that. That's how we do. This is very standard. You do this in undergraduate physics, and that is that it is a function of time alone. Right? In general, this could be a function of position and time. Right? Position, time, and in principle, velocity also. For that matter, why not acceleration? Right? It can depend on various. Since it's derivative, it is not common to write those things. So let's say it's just also R and T. It's understood that it could depend on derivatives also. But there's one simple feature that if it was just a function of time, not a function of position at all, then that's what typically we do in introductory level of physics. And third, it could be that there is some at least simple scenarios here is that it's a function of position alone. It is not a function of time, it is a function of position alone. And gravitational force is a classic example. We have, it's not even a vector relation there. It is dependent on the magnitude of r, right? It is not dependent on the position vector, doesn't depend on the vector r, it's just the magnitude r that depends on. And fourth could be that it depends on velocity alone. And these are, I shouldn't say that this is a complete classification. Of course, the most complicated is any kind of force could be there, but these could be some simple scenarios. And at least in these cases, it is easy to solve. There's a standard prescription that you can make and try to solve it, especially the position-dependent forces. It's kind of nice that then the energy conservation comes about. Let's stick to one-dimensional motion here, just to give the idea, but most of this goes through in generalized 3 dimensions also with some vector properties involved. So let's do the simplest example of f is equal to constant, right? So if it is case 1, if you have case 1, let's put force to be a constant. So acceleration then is equal to a constant force divided by mass m. It could be anything. Let's call this g, right? Because in the classic example we have g. So let's just label them. Even if it was not g, we can always call that some parameter g. Let's say this is going in a straight line. At least in this case, it doesn't even matter. It's the same thing that goes on. So let's say it is rectilinear, right? Just for simplicity. And then you have dv by dt is equal to g. Okay? That's the simplest equation at this point. And integrate this out, and you get v as a function of time is equal to v naught plus g times t. That's how we will integrate, and so this will be an integration constant, and there's an interpretation that at t equal to 0, v naught is the initial velocity, right? Straightforward. Integrate it again. So this is now the x by dt. Integrate this again, and you get x as a function of time is equal to x naught plus v naught t. When you integrate a linear time, you get t squared. And again, you have the interpretation that x naught is the position at time t equal to 0. Very straight forward. Extend this a little, go to case 2. Again, not very hard at all. Right? The only difference will be now you have the acceleration, which is a function of time now. This is force as a function of time divided by m. Again, let's call this g. Let's keep calling this g, but this time we shouldn't get confused that this is not a constant. We shouldn't get confused that we are using the same parameter, but with understanding that it's a function of time. It's just a notation that it doesn't mean that it is the acceleration due to gravity. So again, let's keep it one-dimensional. So let's say assume rectilinear. Motion. Is it called rectilinear or linear? Why is that rectilinear? Let me not say that. I'm not sure. Okay, let's say assume one dimension. What's the meaning of rectilinear, by the way? Any idea? No. Okay. Yeah.
I think
Okay.
it's like the axis of x and y. They're both perpendicular to each other and something like that, probably like rectilinear coordinates.
Yeah, that's what I thought. But then why is the word linear there?
Maybe these coordinates are, the axes are like a line. I don't know.
Yeah. Just I got a little confused there. So maybe, yeah. Okay. How about this? Yeah, we have a quiz. So Harsha, we were so in the course outline. So we will have a quiz a method. So 10% of the course is dependent on what we call quiz.
Okay.
So what that means is that right when there is a discussion in the classroom or for some purpose, you come up with a question. So for example, today's question could be, right, and it's straightforward. So this is quiz. Check up rectilinear. What's the meaning of rectilinear, right? It could be as, I shouldn't say mundane, it should be as straightforward as this. Okay. Or in the first class, it was look up brachistochrone, right? What is the meaning of brachistochrone, right? Now, I should warn you that when I give a quiz, it is an open-ended question. Sometimes the question itself might be wrong, right? Because it comes up in a discussion. And so frame your own question, pose your own question, and answer it using any source on the internet. And as far as assessment goes, don't spend more than 10 minutes. If you want, you can spend 5 hours on it. It's up to you if you get interested in it. But as far as assessment, just for the sake of submission, don't spend too much time. The grading will not be for the correctness. It is just for the submission.
Okay.
Right. So that's just for the sake of letting you know. And if you look up, it contributes to some part of the curve also. So that's just for it. Information. Okay. Okay, so if it is time dependent, then we have, again, let's keep it one dimensional. So then that is everything is happening in a straight line. So we have dv by dt is equal to g as a function of time now. Right? This time when you integrate, so you will say this is dv is equal to g of t times dt. Correct. Integrate both sides. So we have integrate both sides, and we have to talk about where to where. So let's say you go from t equal to 0 to t. But then if I call this t, then I have to be careful. There is an integral variable here, and there is an integral. So I should change this to t prime. Right? Integration variables are dummy, and I'm changing the limits. So that's 0 to t now. What happens to the velocity at time t equal to 0? Let me say the velocity was v naught and the velocity goes to v, right? So that's the velocity at time t equal to 0. So we learned that v of t minus v0 is equal to, unless I provide the actual function here, I cannot do that integral, but it is clear that in general, if this integral is doable, then we have a specific function of time. Velocity is dx by dt, so we can immediately say this is also equal to v naught dt and plus. Let me, should I name this? Yeah, let's keep it as it is. And we have 0 to t dt prime and g of t prime. And I have to integrate with respect to t now. Again, do another integration. So this is dx is equal to v naught dt. Let's do the integration from 0 to t. I have to change this variables again. This is dt double prime now. This is 0 to t double prime, t prime, and g t prime. Just keeping it very general. So this is 0 to t, and this could be at x0 to x. Right. And again, we see that this is x as a function of time minus x naught is equal to v naught t plus, do this twice. I think it is very clear that if it is a constant, you will get back here our earlier equation. And we won't explore this too much. Like for simple functions, it's clear how this will work. So that's just for two simple cases. You have first case, the second case. The third case is more interesting. It's again for a general force, it is always possible to do that if it is a position dependent quantity alone. So let's investigate that, and that will lead us to the homework problem also. So there's a homework problem on the pendulum. The pendulum problem is a classic problem. Everywhere we see that, but often we never do beyond small angle approximation. So it's good to go beyond small angle approximation at this stage. So I'll motivate that, and that's part of your homework. So let me move the camera. Is this readable, Harsha? Like Ken said, it's great. You're muted, yeah.
Oh yeah, it's fine. It's readable.
Okay. I know it is small, but hopefully, let me know. I can zoom in also. That's the point I was trying to make. But okay. So if necessary, I can zoom in. But just let me know. So let's do the next case, and this is when the force is equal to a function of position law. Again, let's keep it one-dimensional, but when we come back to the pendulum problem, pendulum swings in 2 dimensions, right? It happens in a plane, so we have to use the vector, but it almost goes through exactly the same case here. But for simplicity, let's keep it as a function of position alone, or function of one dimension alone. And we again have mass times acceleration. So it's one dimension, so it's a dv by dt. So, what do I mean? Let's write this as, this time, second derivative of x with respect to dt squared is equal to f of x. That's what we want to talk about, and let's keep that reasonably general at this stage. Example could of course be a gravitational force when a stone is dropped from a very far away point. Correct? Let's think of a situation where it is dropped from many kilometers, let's say 10 kilometers or something, a meteorite falling straight down into Earth, and let's say it is falling straight down, radially down. So that could be an example, but let's see at least formally how you would go. The trick here is that I'll multiply this by, so we want to solve for position or velocity to begin with. So let's multiply by velocity. So that's the trick in these cases, and in generally it works. This d2x over dt squared is equal to f of x times dx by dt. Okay. Change this to let's say, notice that this is a velocity and an acceleration, so you can see that, let me write this here itself, right? So if you do time derivative of dx by dt times dx by dt, so let's say m times dx by dt squared, right? So you will recognize this to be as kinetic energy, right? And let me put a half there. Notice that if I operate this, I get the chart left hand side. That's because what this term is that d by dt of half mv squared, right? That's equal to half m. So there is two velocities there. I can either differentiate the first velocity or the second. So there are two terms there. So that's 2 times v. That's the differentiation of v squared. But v is a function of time. Using chain rule, we have dv by dt then. And you get m times v times acceleration, right? Which is what you have on top. If by any chance, if you were doing 3 dimensions, since we will do that in a minute, this will be v dotted with v. And you get this to be the same idea there. So half times m times v dotted with acceleration. Get rid of the half, right? Dotted with that acceleration. So instead of multiplying by the velocity, you will take a dot product with the velocity. And on the right hand side, then you will take the dot product with the force, and you might realize that, oh, that's like a work done, right? Force dotted with. What is force dotted with velocity in introductory physics? Like, what is that quantity called? Check the dimensions.
It's the power.
Power, right? Yeah. So the force times displacement will be work done by time. So this is the power, right? So this is power. So it is rate of change of energy. And if it is a conservative force, you can take this out. So that gives you the hint there that there is some energy conservation equation involved here. And just to clarify that better, so let's go to the, so this is equal to, so this is f, so this is f of x, dx by dt. Let's do this for a specific example. So let's do an example now, so that we can see the energy conservation coming out clearly. Just that there is, I would like to take this time derivative out, but then I have to know what quantity actually gives you that. Oh, yeah, I think let me do this in a general way, right? So let's say, so let d by dt, so there exists a quantity which is called the potential energy. So there is a potential energy to this, be equal to, so you can either differentiate with u, or you can differentiate implicitly with respect to x. Correct? So this will be using chain rule, du by dx and dx by dt. And since I'm defining this, let's say this is, so u is, there's a negative sign missing here, right? Help here, so that's minus, and yeah, so let me define, so this is the definition. Let me define f of x to be minus u by dx. Remember, whenever you have an energy, force is the negative gradient of energy, right? Rate of with respect to position, at least. So that's gives you, this is minus f of x dx by dt. So we can substitute this in there, and we learn that this is kinetic energy of m v square. Let me write this as v square just for clarity. There's a minus u of x there, so when I bring it to the right hand side, it reads this, and that's equal to 0. And that clearly tells that this quantity is conserved in the sense that it doesn't change with time. So that means that's a constant. So we have half mv squared plus u of x is equal to a constant. And let's say that's the energy. Let's define that to be the energy. But the moment you write that, and this is a constant, right? This doesn't change with time. This is a constant. The moment we see that, we can actually solve for velocity. Remember, our goal is that given a force, can we solve for the velocity? Yes, now we can immediately do this. So velocity is, take this to the other side, and we have 2 over m times e minus u of x. Right? I did that. Correct. So that's dx by dt 2. So we now solve for velocity. So we know that if we know this, that oh, there's a square root there. Sorry, square root, because I solve for the square, so I get a square. So if I know this function, immediately take the square root using conservation of energy. You know the velocity. This is what we do, right? Whenever there is an inclined plane problem, we realize very quickly in introductory level physics that conservation of energy is a significantly easy process to solve. As far as an energy is conserved, and that is friction, it is not conserved. So this is not always easy to use. If the energy is conserved, then you can do it. But this can also be used to now solve for the x, right? Once we know this, we can actually integrate this out. So let me write that here. So x over 2 over m times energy minus of u of x square root is equal to dt. Okay, that's a correct relation. And integrate this on both sides. So let's say 0 to t. And let's say at time t equal to 0, its position is x0. And at time t, its position is x. And then I should switch my integral variables to prime, right? Otherwise, it will be confusing. And if this integral is doable, then we immediately get, and if we can invert this x as a function of time, we get the position also as a function of time. So let's quickly do this for an example of this meteor falling into on the surface of Earth. So a very simple example. So we have the surface of the Earth as a sphere, and let's say the radius of Earth is r, and so this is, everything is happening in a straight line. That's not how typically, it's very rare that something will fall radially inward onto Earth. It's typically a two-dimensional motion, but if it was radially, hypothetically speaking, you start from some r initial, right? R is equal to r initial there, and right when it reaches the surface, its position is r. Right? It could fall all the way from infinity also. So if r initial was infinity, then we can find out what happens so when something reaches right on the surface. In that case, the force now is a function of r now instead of x. Think of it as r. And the force is the gravitational force now. So it is the mass of Earth. So m is the mass of Earth, let's say. And this could be a tiny mass there. Let's say the mass of the meteor, that's a small m. So g m over r squared. But this is inward, so there's a negative sign with it. So it is attractive force, that's inward. So our equation becomes m d2r over dt squared is equal to minus g m over r squared. Use the same trick that we did at a very formal level on the left hand side. Multiply by r by dt on both sides. Multiply by the velocity on both sides, and that gives us r by dt. But in this case, it's very clear to see what this is equal to. If I were to differentiate 1 over r, notice that d by dt of g m over r will be equal to, first differentiate r 1 over r, which gives you a 1 over r squared. And then you have to differentiate using chain rule, the position itself. So that's dr by dt. Am I going out of the board? No, I'm still there. Right, so this is total time derivative. I can use that. This is the kinetic energy as we did there. So this is a total time derivative of half m dr by dt squared. And the right hand side is just d by dt of g m over r. Notice that I'm missing, it's better to write this as minus here and a minus there, Why is that? Because then this is the potential energy, right? Potential energy is a negative. It's like gravitational potential energy is attractive, so that's a negative sign in there. So just to catch that, I'll put the negative sign, and this negative sign I'll use it to move it to the left. So then energy is conserved. So we immediately have half m dr by dt square. Of course, the small m cancels out, right? So we know that in gravitational physics, it is mass independent. The motion is m independent, at least if one of them is at rest. Right. So that's dr by dt square and plus gm, no, minus, right? Sorry. Minus, I meant to write that, over r, and that's equal to energy, which is a constant. But now, if it is a constant, so let's say this is constant E. Right? Now let me put in some initial conditions there. Let's say that the mass starts from 0 velocity, so at time t equal to 0, so velocity at time t equal to 0 is equal to 0. Right? So it starts from 0 velocity, so we drop. So the meteor was just sitting there, very unrealistic, but let's say that it was just at rest there, and then it falls. In fact, it could be realistic in the sense if you take it all the way to infinity, then you could imagine a situation where if it was at rest and then it is just falling in. So, so if that is the case, then the energy has to be is a constant. So at that particular point, this term is 0, and this is just R initial. So the total energy is equal to Gm over R initial. If it was at rest at t equal to 0, wherever it begins, it is at rest. And in that case, this can be rewritten, right? And we can get our dr by dt, the velocity term, immediately. Let me cancel out the m's right away. And what I have is 2 times Gm over R minus Gm over R initial. And I have to take a square root. And we can, in a few minutes, I will discuss what we can do about the position integral. But let's, for a moment, sit on this and see there's an interesting feature here. Let's say, or just a point one can mention. And erase all this. So let's say that, yeah, let's go back to this kinetic energy equation, and let me ask if it started at infinity. So if our initial was infinity, then, and if it starts from rest, right? Our initial is infinity and v initial is 0, right? Is equal to 0. Then we notice that the right hand side is 0. So that's half m v square, velocity square, minus g m over r is equal to 0 on the right hand side, because our initial here is infinity. And that, oh, so that was a small mass also. So m cancels out, and we immediately get v is equal to gm over what is this? 2 times gm over r, correct? Let me write this slightly differently. So let me say this is gm over r square and multiply by r itself. Or actually, not to confuse you. So let's say, just to show that it's I'm not manipulating anything. Let's say velocity at the surface. So it starts from infinity at the surface of Earth. Right? So it starts all the way from infinity and reaches the surface of Earth, and the velocity at that particular point. So let me call that velocity at the position r, right? That's equal to 2 times g m over r. No doubt about that. But now let me manipulate this. Oh, did I make a mistake here? Mistake? This was a square root, right? So I've been missing that a couple of times. So that was a square root. So this is also a square root. But let me rewrite this as r square times r. Just check rewriting, and then you will recognize this as what is capital G, capital M over r square for Earth? Something familiar?
Small g.
Small g, right? So that's 2 times G times R. And that should, if you observe this, this is an interesting result in the following sense. Notice we are not talking about constant acceleration here. We are talking about a meteor falling all the way from a varying acceleration. But now think of a following problem. You have flat Earth, let's say. So this is flat Earth. That means to say that Earth is really flat and really huge. And so that means that G is constant now, right? G is constant. And in that G is equal to constant, let's say that you drop a mass from a height of r. So notice in this problem, r is the radius of Earth. In this problem, I have a mass falling from a height r. And in that case, we know that potential energy is 2g mgh, correct? And you will immediately get that half mv squared, the kinetic energy that you will gain here if you drop it from rest, is equal to mgh now, which is r. So velocity is 2 times g times r. So remarkably, entirely two different problems, the amount of velocity you gain due to the gravitational force of using Newton's gravitational force, which is a varying gravity, all the way from infinity, it keeps increasing slowly because at very far away, the gravity is very weak, right? But it keeps slightly gaining energy. And by the time it gains energy at the surface of Earth, that's the same amount of energy which you could have gained just by dropping a mass in uniform gravity at from a certain height r. Just a correspondence there, nothing deep there. It's just a fact that these are decaying functions. Integral of a convergent function can equal something else. So I don't think fundamentally deep there, but it's kind of a nice little exercise there. Okay, so that's velocity, but let's go back and actually talk about position a little. And there's some non-triviality in that, and we will talk about, or at least let me emphasize, is that here. So let me start from dr by dt there and write that as the following. So this is the same as 1 over r minus 1 over r initial. And that's equal to 2 times g times m and dt. same equation for this problem that reads that. Again, do the integral 0 to t, and this will be when time is 0, position is r initial, and when the time is t, let's say it is r, and now I should say r prime, right? Okay. The right hand side is the time taken for the fall, right? It starts from time t equal to 0, and how much time does it take to fall? And that's equal to 2 times g times m times t. But on the left hand side, if you were to do this, especially for r initial equal to infinity, this will diverge. Okay, and that is a correct answer. If you ask the question, how much time it takes to start from infinity for something to reach the surface of Earth, if you start from rest, how much time it will take? It will be infinite. Okay, so that's not trivial. So just to point that out, so that leads us to another quiz problem. So let's say that you have a, so this is half, like this could be any surface, but just to make this clear, so let's say this is minus kx squared, like half kx squared, let's say. Right, so this is position on the right, and this could be potential energy on the right, or it doesn't have to be a potential energy. Think of this as a real actual mountain, right? So in that case, typically the potential energy is a good representation of that. Now it is clear that if you have a mass sitting here on top, it is going to be unstable, right? And that means to say that even a small tiny delta, it will fall off here. It will start rolling and it will start fall off. And forget about rolling, let's say it's frictionless, so that you don't have to worry about the rolling part in here. But now let me reverse it, okay? And we can also calculate the time it takes to go from there to here. Now let me reverse it. If this is the velocity v, like if I throw it, push this mass with exactly some velocity v, so that it reaches the top, right on the top, and it has to just reach the top. Of course, it is unstable. It may not stay there. If it is slightly less, it will be delta less or delta more. And if you were to calculate this time, it will come out to be infinite. Time will come out to be infinite. So look up. So this quiz problem is for you. Again, remember that quiz problems are open-ended, and leave it. Just try to think about it. And this is called sojourn time. And sojourn, I think, I don't know how to pronounce it, probably sojourn, I'm not sure, is when you just take a rest for a long time. I think that's what a momentary rest. Okay, so look up that time. And that leads, so that's a quiz. I'll leave that open, and this is, so in that sense, this integral can be done, but then there are divergences associated with that. So calculating the time is not the most convenient thing. But for the pendulum, we will do this. So let's go to pendulum, just a few discussions on that. So a pendulum, so this is a pendulum and not a small angle approximation pendulum. So let's say this is, that's your pendulum, that's angle theta. Okay, and the time period of a pendulum is, you start from angle theta, you come to angle 0, so that's 1/4 of time period. Then it goes back all the way to minus theta here. It'll reach a maximum here. It will take the same amount of time, then come back to 0 and then go. So 4 times this quarter time period. So this start from any point, go all the way, make one full cycle. That's called the time period of the pendulum. And we know that for small angle approximation, the time period is fixed, right? It depends only on the length and the acceleration due to gravity. But what if theta was large? So if theta, so let's say this is theta max, that's the maximum position in each start. So for theta max is equal to pi, right? That means you take it all the way to the top, right? All the way to the top, and then leave it. What's the time period? Right? What is the time period? Are you familiar with this problem? Ken, Hatra?
No, but at theta equal to pi, won't it just simply stay like that?
Yes, good. But it's unstable, right? So let's say in the limit theta tends to, how about this? Yeah. In the limit.
Okay.
Yeah. And this is non-trivial in the sense this approaches infinity. In fact, if you started from there, so it will go all the way and then come back here. That's it. So you will never reach there. So that's not a right away obvious, correct? Why should that be infinity? And that's part of your homework also. You will see that why it is. It's basically a function, if you know the property of the function about. So let me talk about, so this is now coming to the homework problem, which follows pretty much the same strategy, but since it's a two-dimensional motion, we have to do a small variation of this, but otherwise it's exactly the same. Any questions as of now on whatever I said, at least strategy-wise or the algebra-wise? Any comments or anything you want to say? Okay, so let me proceed and do the pendulum now. This is part of your homework, but I'll construct a good bit and you can do the analysis. Okay. So this is let's call it, it's still called a simple pendulum as far as I know, but no small angle approximation. So simple pendulum as I drew earlier. So that's your pendulum. And I think in your homework, I used the angle phi here. That's angle phi. It's measured with respect to the vertical, the negative y-axis. This is a pendulum in the sense one should think of this as a rigid rod. So this is a rod, but then make it massless. That way you can actually take it all the way to pi. Otherwise, it will just slack, right? So just to have that property, keep this a massless rod. And let's say it has a length L, small l. And then there is mass M, and there is gravity acting downward. So there is force acting on this. So that's mg. And there is a force of tension, that's T. And let's try to use the same method that we did there, but there are various ways of getting the equation of motion. You can use the torque equation and immediately get it in one step, but let's do the method that we just did. So we have mass times acceleration is equal to the two forces, which is mg plus the force of tension. That's Newton's law. Vector sum of the forces acting on the mass m is equal to the product of mass and acceleration. Okay, the idea is to multiply it with the velocity. So we have mass times velocity dotted with a. This is equal to mass times velocity dotted with g plus velocity dotted with the force of tension. All right. Now, velocity for a pendulum is always tangential. Right? So velocity. So we have this is going along a circle, right? And the velocity is tangential. If that is the case, immediately we know that force of tension is always radial because it's along the direction of the string. So we know that this is equal to 0. This is also true because this is a force of constraint, as we will see later on. That's also the reason why the force of tension is always perpendicular. Okay, so what we learned then is that velocity dotted with a is equal to velocity dotted with g. Left hand side is kinetic energy, so that's half d by dt of half mv squared, as we saw earlier. That's v dotted with v if you want, and that's equal to v dotted with g. What is v dotted with g? Let's look at this. So that's your angle phi. V dotted with g is v times g, and what is this? Cosine of 90 minus 90 plus phi. And cosine of 90 plus 5 is sine phi. So it's minus v times g times sine of the angle phi. Again, notice what is happening here is that velocity acts as a vectorial direction in this tangential direction. So we are taking the component of this Newtonian, of the Newton's law in the direction of the tangent vector. So that's what we're doing. And the radial directions are not really an equation of motion, it's an equation of constraint. That's what is happening there in this projection, if you want. So that's, and also notice that since the velocity, this is going along a circle, like this is constrained to move along a circle, velocity v is actually equal to the length L times d phi by dt. Is that correct? Yeah, that's correct. Right, because the radius doesn't change. Usually there are two pieces to the velocity. Either it can change the radius or the angle. So radius is fixed. So v is L d phi by dt, right? So this is minus g sine phi times d phi by dt. But that's the same as the total derivative of g cosine phi. Because if I take the derivative with cosine, I get minus sine phi, but then phi has time dependence, implicit time dependence. I have to take the derivative with phi also. So, and if you notice, if I were to multiply by m there, that's nothing but the potential energy, mg cosine phi. Cosine phi is pretty much the height that is being brought up. Oh, there should
We are
be an
missing.
L there, right? Oh, yeah, that's what Harsha, you were trying to say.
Mhm.
Yeah, so there is an L there, right? So there's dimensional reasons. So there's an L. So L there, because L cosine phi is the height, right? If you were to notice, L cosine phi is a projection of L in the vertical direction, which becomes a height, and we know that potential energy is mgh, right? Yeah. So this is d by dt, and am I missing something? No, I guess not. Yeah. So this is d by dt of L times g, and there should be an m also, right? Here there is no m because I already cancelled out the m. Right? So this is Lg cosine phi. Correct. So we have half. What am I doing here? Help. Yeah. So this is okay. So I do again. This is a constant, right? So this is v squared is equal minus, right? Minus Lg cosine phi is equal to a constant, which if I were to multiply by m, then I can say it is energy. Right, so that's energy. So that's why I put in the mass back so that I can identify it as the energy. Otherwise, it's just a constant. It is energy over the mass. But what is that? Constant energy. Again, we need an initial condition, right? We say usually at t equal to 0, what is the case? So let's say this pendulum is released from rest from a maximum angle, right? And the maximum angle, let us say, is phi naught. So phi naught is the maximum angle of release, and velocity at that point is 0. Right? So if that is the case, so that's equal to 0. This is equal to minus mg L cosine phi naught. Same idea as what we did earlier. So if I put this onto the right, I can cancel out the mass, and what we get is velocity v is equal to velocity v squared is equal to L times g, L times 2 times L times g times cosine phi minus cosine phi naught. Did I get the signs correct? I think so, right? Minus, yeah, I think so. Half mv square is equal to mgh, but I think that h here is downward, so I think it is okay. Yeah. But velocity, we remember, was L times d phi by dt. So this is the same as L squared times d phi by dt squared. So I can divide out by that L, and what we have is d phi by dt squared, let's say, is equal to 2 times g over L times cosine phi minus cosine phi naught. If this was a small angle approximation problem, then you would immediately replace cosine phi with 1 minus 1 minus phi square over 2, because then it becomes a simple harmonic motion, and then you will identify g over L with the time period. So let's think of that. So let's define omega naught to be equal to g over L or omega naught square to be G over L. In that way, the time period T will be equal to 2 pi over omega naught. Notice that's a square, so you need to get a square root of that. And that's a standard time period for a simple in the small angle approximation. If there was a pendulum oscillating, that's the time period of that. In that case, we can write d phi is equal to 2 omega squared, and that's cosine phi minus cosine phi naught, and that is a square root of this times dt. So this is the same as d phi over 2 times cosine phi minus cosine phi naught. That's equal to omega naught dt. We would like to calculate how much time it takes to go from here all the way back, but let's say that we would calculate only from phi naught to 0. So we're releasing it from a maximum point. It goes all the way to the bottom. So the time period will be 4 times that, because it has to go 4 times that for the time period. And this will be t by 4, right? So this is sorry, I was meaning that on the right side. So let's say start from time t equal to 0, and the time it takes to reach there, we will call it capital T over 4. So that's the time period or the time taken for that 1/4 of the revolution of the cycle involved. And in this case, angle goes from phi naught to 0. So we have, if I move this to the left hand side, omega naught t over 4 is equal to, I have, let's say, this is phi naught to 0, and we have d phi over 2 times cosine phi minus cosine phi naught. So if we can do this integral, we are good. We can actually calculate the time period. But this integral doesn't, we don't have a simple answer for this integral. This turns out to be an elliptic function. So notice that whenever you might have come across problems where you cannot really do integrals using simple methods like substitution method and so on, you come across those problems, and this is one of those integrals which cannot be done using standard substitutions. In fact, we don't know what this is, but that doesn't matter. For each phi naught, I can calculate the number associated with that, and that's what you do. So this integral turns out can be written in terms of what is called an elliptic function. So what is an elliptic function? So this is like your sine and cosine function. What are sine and cosine functions? It's basically a series, right? And since we know so many properties of that function, we know the double angle formula, we have all these trigonometric identities. It's a very well studied function. Elliptic function is also reasonably well studied. We don't have as many identities as we would like to have, like trigonometric functions. So in that sense, this is defined as, so let's say this is confusion. So let's say this is x. So that's equal to 0 to pi by 2 to d theta over 1 minus x squared times sine square theta. Again, this integral cannot be done, but you can calculate this. These are convergent functions. For each value of x, you can actually calculate k of x. So this becomes a function then, and the functional form for this is, I should also point out that x is less than 1 in this case. And if you were to plot this function x, or function k as a function of x, it starts from 1 and it grows. And it goes to infinity very quickly. So that's x equal to 1. And it actually can be extended backward also. So your homework problem, so this most of this is part of your homework. Try to redo it. Your homework is to go from here to that. Right? I give you the substitutions that is needed. It's reasonably straightforward. And you have to plot this time period that you calculate as a function of the angle phi naught. And it is good to know how much error do we make. Like we typically make small angle approximation. How much error do we make in this approximation? And it turns out that even if you go all the way to 60 degrees, you will notice that the error is not significant. Significant in the sense when you're working in a lab in the preliminary, unless it's a precision-based experiment, 10% is a good amount of error. It's a tolerable error if you want, and it will come out to be less than 10%. So one of the homework problems is that if you were to release the pendulum from 60 degrees, and if you were to actually use a small angle approximation versus this exact method, well, how much error do you make? Like is it 1% error? Is it 0.3% error? Or how much error do you make? So you have to evaluate this integral and calculate it at a certain value and compare it with the approximation value. And of course, you have to calculate this for phi naught equal to pi also. Not calculate, at least analyze what happens. And as I mentioned, it will come out to be infinity. So that should help you with the homework also. So hopefully this was useful. I'll stop at this point. Any comments or questions? So Ken, have you seen these things before, roughly?
Yeah, for sure.
Okay. Harsha?
Yeah. We talked about elliptical functions also, right? At some point.
Oh, maybe.
In another course.
You took ENM with me, right? Yes. ENM, when we're doing magnetic field, I talk about elliptic functions. Yes. Mm-hmm. So yeah, that should help. Yeah, that should help a lot actually. Good. Okay, thank you. Okay, Ken, bye. Close.